So now we're going to look at the proper way to go about solving the median, right? So we're going to go ahead and have a set of values over here. We will have, let's go with 5, 15, 8, 3, 7, 1, 9, 10, 6, 7, 12, 14, 2, 16. I could put one more. We'll go with 19. So this value over here, this is, I guess, x over 1, it's the first value. And we have another value over here. We'll call that x15 because we have 15 values written over here. Now, looking at this straight up, you could probably figure out what the median was in, I guess, 30 seconds to a minute by figuring it out. But we want to actually have a procedure to go about doing this, because just looking at it right now, it's not like an ordered list where you'd pick it out right away, right? You'd figure out what that middle value was, the ceiling of n over 2, and then you'd figure out that value. Right now, we don't know what it is. So how we're going to do this is we're going to start up by asking, is this value over here? Is this first value? Is this x1 value the median? Now, in other words, what is this going to say? We know that we have 15 values over here. The median is going to be the ceiling of n over 2. So what is the ceiling of n over 2 over here? It's 15 over 2, which would be 7.5. The ceiling of 7.5 means you just round it up no matter what. In this case, that would be 8. The 8th position is going to be the median if this was sorted. If that is the case, this means we're essentially asking, is there 7 values less than x1? And we're going to go ahead and check. So let's go ahead and we are going to write our number. And this number here, the first value we pick, the x1, we'll call this the pivot. We're going to have some values on the left and we'll have some values on the right. This is going to get squished because we clearly see which direction this is going to go in. So let's go ahead and start off. So we check the 15. 15 will go over here. We check the 8. Oh, the 3 will fit on this side. We can put the 3. The 7 will go here. The 1 will go here. The 9, 10, 6, the 7, the 12, the 14. Oh, good. We have 1 for the left side. So we're putting the bigger numbers on this side and the smaller on this side. Go ahead and put that bigger. Bigger than x1, and then smaller x1 there, just in case anyone wasn't following along. 16 and then 19. Does this look like the median to you? Well, we don't even need to really count this. We can clearly see that there are not an even amount of numbers on both sides. So this is clearly not the median. We're going to have to do a bit more work. Now, we can tell right here that 5 is let's go ahead and get some more room so we have to work. New color. 5 is the fourth smallest number. We can also know that this fourth smallest number, we need 7 numbers to be smaller than the median, right? So there's 3 numbers that are smaller. So this automatically says that 3, 1, 2, the ones that are on the left side, will not be the median either, right? We need that 7 number. So the setup that we have over here, we have the 5, which is the pivot. And then we have, 2 sets, right? We have a set right over here, right? The set right. And then we have the set left, right? We have these 2 pots of value, essentially, right? These 2 bins full of numbers. And which number is our median, which bin is our median going to belong to? We know it's not going to be on the left. It's not possible for it to be on the left because we already know those values are too small, right? Those values are not going to be any closer to the median than the one that we just tested at our pivot. So it's going to be in the right. So already, sort of like the binary search, we have eliminated some values from the possibility that they will be involved, right? Which means we don't have to have those search runs, which is really convenient. We know that we have 4 values that we've already crossed off. So the fourth smallest value in SR over here, S right, is going to be our median. Let's go ahead and take a look at some pseudocode, right? So you'd essentially call this, inductively or recursively, I should say, on the right side, but now instead of looking for the 8th position, you're looking for the 4th position, and you could keep repeating this process over and over. So we are going to look at the pseudocode behind this, right? The pseudocode is going to give us the process that we're going to run through, and you can see how this method is going to save us time just based on the fact that we are going to be able to skip over some of the searches we might need to do. So we're going to go ahead and we'll call this find median. And we are going to have our set, and we're going to have the value that's going to, the k value, which is going to correspond in this case to the position of the median. So we're going to go ahead and say that if the size, this is going to be the size, right? If we have those two lines, that means we're talking about the size of the set, so the amount of values in there. If the size of the set is equal to 1, output k, sorry, not k, stupid, output x1, right? Remember, we'll go ahead back here. Remember, the set here is going to be x1, x2, dot, 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 all the way to xn. So this is our base case, right? If there's only one element, that one element has to be your median. It's the center value by definition. So we will have that base case to catch us to stop our recursion. Then we'll have else. We'll have the left side. We'll go ahead and define that left side as xi, part of our set, where xi is less than x1. So all the values that are less than the x1, remember, we're picking that first value. Everything that's going to be less than that will go into the right side. And then we'll have SR. It's obviously going to correspond to the left side, and this will correspond to the right side. XI, part of the set, is going to be the ones that are greater than x1. We'll go in that one. And obviously we're assuming that x1 to xn, all these numbers are going to obviously be distinct in this case. So now we have two options that we have over here, right? So we can go ahead and say, let's go ahead and get some room. If this is obviously going to be the size, the amount of values inside of SL is equal to k minus 1, then this means then the pivot is what we want, right? If we find that the left side is going to contain one value less than what the median position is, then that clearly means the pivot is our value, right? It's still part of the pseudocode over here. So I'll go ahead and actually write that on the side over here, right? Then pivot is median. So if this is the case here, the pivot will be your median. And what do we return? Here we'll go ahead and we will be returning that value, right? We'll just go ahead and return x1, right? It's the value we start off with. We'll return that value. Go ahead and scroll down a bit more. Have another if statement. If it is found that the left side is greater than k minus 1, which means you have to look inside of that bin of numbers, right? That means your median is hidden inside of the left-hand side because we now have more values than the median position subtracted by 1, which would normally be obviously in the case that the median was actually selected as your x1. You got lucky, then you'd have one less value on the left-hand side and obviously one less value on the right-hand side for your k. If you have more than that, then that means you have taken more values in. You have more values that are lower than the median, which means, or the test median, if you will, the pivot, I should say. So in this case, let's go ahead and write that median will be in there, need to recurse it. So we will need to call something recursive inside of there. So we are going to go ahead and we are going to use our find median algorithm. And now we are going to call it. So this time we'll call it on SL, so the left-hand side set. So all the values on the left. And we are going to call it, what are we going to put over here? We are still going to put K. We're still looking for the kth item inside of there. Okay, so we're going to go ahead and we are going to keep moving in this direction. So still looking for the kth item, and now we'll have another if statement, obviously. So in the case, the last case, where we find that SL is less than k minus 1. Now it's obviously, where is it going to be? Where is our median going to be hidden? Wrong color. There we go. Median is now SR. It's now hidden in the SR bin. So it's on the other side, which would mean that you need to recurse, but now with more specificity. So what is that going to mean? So find median. So we're going to call our algorithm again. And we're going to call our method again. We're going to say find median. Call it on the right side this time. And now you'll call for the k minus the amount of values in the left-hand side subtracted by 1. So that's the values we are going to use right now, because we already know that's not going to be in a certain spot. So that is the algorithm for this whole process, right? It's pretty simple. If you run through it a few times with some dummy information, if you will, just write down an unsorted list and just pass it through this, it's going to make some more sense. We're going to look at the runtime in the next video. I hope this made sense. This last part here gets a bit confusing, but if you look back to what we worked on a bit earlier with the practice problem, and if you would go through that one that we had, then it's going to come together a bit more. So look at the runtime in the next video. This is going on a bit too long, and I want to split these videos up.